In this video, you will discover how the Vikings built flexible, storm-resistant houses, an architectural system confirmed by excavations at Stone, Iceland, where archaeologists found walls capable of shifting millimeters without fracturing under winds exceeding 120 kilometers per hour. They did not try to overpower the climate. Instead, they designed with it. How did they make timber, stone, and turf work together to survive centuries in the North Atlantic? Today, many of these solutions remain in use because they still work. Chapter 1. The foundation that kept a Viking house from rotting. Modern audiences often imagine that the greatest threat to a Viking house was the force of the North Atlantic winds. However, archaeological evidence reveals the opposite. In Norway, Iceland, and the Faroe Islands, the most common cause of structural failure was not the wind, but the constant moisture rising from the ground. Rain soaked the soil, cold temperatures kept it saturated for long periods, and any timber in direct contact with that moisture decomposed in a few years. For this reason, Viking builders began by solving a fundamental problem. The foundation had to remain dry for decades. This necessity explains one of their most practical and ingenious solutions. Findings at the settlement of Lonso Meadows in Newfoundland and at the reconstructed farms of Thjodveldisberg in Iceland show the same principle repeated with remarkable consistency. Instead of placing the walls directly on the soil, the Vikings used a system of dry stone. They selected flat, hard, stable stones and arranged them without mortar, adjusting each piece patiently until achieving a level and continuous line. The height was not the priority, uniformity was. An uneven base transferred stress to the timber walls and created gaps that let moisture in. A level foundation distributed weight evenly and prevented torsion. This dry stone layer did not form a tall wall. Archaeologists describe it more accurately as a structural belt outlining the building's perimeter. Sometimes it barely reached the height of a clenched hand, yet its purpose was critical: to keep the timber off the damp ground. Elevating the first timber just 10 centimeters extended its lifespan dramatically. Viking carpenters knew this through generations of observation. Long before any scientific study of capillarity or fungal decay existed, air circulation was essential to the system. Small gaps between the stones allowed wind to enter and dry the underside of the timber. This detail was not a flaw, but an intentional feature. Timber should not be sealed tightly. It needed to breathe. Excavations of buildings from the Viking Age in Norway have revealed remarkably well-preserved lower beams, supported precisely because natural airflow kept them from remaining wet for long periods. In a climate dominated by humidity for most of the year, this combination of slight elevation and controlled ventilation allowed the structure to endure for decades. The first timber placed on this stony foundation was known as the fundamental beam. It supported the weight of the entire wall and had to be chosen with exceptional care. Builders preferred straight timber, free of knots, usually taken from the lower section of pine or spruce trunks. This was not an aesthetic preference. These parts of the tree had denser fibers and greater resistance to moisture. The fundamental beam rested directly on the dry stone belt, secured by nothing more than the weight of the structure built upon it. It required no nails. Gravity and precision were enough. Preparing this fundamental beam followed a practical process. The bark was removed carefully because bark retains moisture. Afterwards, the timber was left to dry for several months, often raised on posts so air could circulate beneath it. The internal moisture of the wood needed to be reduced enough to prevent twisting when exposed to seasonal changes. Anyone who has worked with timber recognizes this necessity immediately. The Vikings had no drying kilns, but their natural method was suited to the northern climate. The audience has repeatedly expressed frustration that many videos do not explain anything practical about the real building process. This chapter responds directly to that concern. The dry stone elevation was not a metaphor or an idealized technique. It was a reproducible system, confirmed in multiple archaeological sites and fully understandable to anyone with experience in timberwork or traditional construction. Moreover, it demonstrates that Viking builders did not rely on brute strength, but on a deep understanding of their environment. There was no need for a complex invention. Simply keeping the wood separate from damp soil and allowing air to move freely was enough. The dry stone base also provided an additional benefit often overlooked by modern viewers. By slightly elevating the structure, it prevented small animals, rising ground moisture, and even cold drafts from penetrating beneath the wooden floorboards. Although it was not a perfect form of insulation, it was a significant improvement in a region where extreme cold could be life-threatening in winter. A Viking house was first and foremost a tool for survival, and every design decision served that purpose. Choosing the location for construction was also essential. Contrarily to popular depictions that show houses standing just a few meters from the ocean, the archaeological reality is different. Most homes were built inland on slightly elevated ground that avoided flooding. Selecting the right terrain was as important as the building techniques themselves. Damp soil doomed any structure, no matter how well built. Part of Viking knowledge involved reading the landscape and predicting how water would behave during thawing seasons or storms. Thus, the first practical secret of Viking houses was not complex joinery or advanced tools, but an elemental and effective solution. Isolate the timber from the ground with dry stone, precise leveling, and controlled ventilation. This seemingly simple base allowed the entire upper structure to function for decades, even under extreme and shifting weather. Without this step, no other technique would have mattered. In the next chapter, we will see how these foundations supported walls capable of moving without breaking. Chapter 2. Walls that move. The flexible engineering of the post and plank system. After securing the foundation against moisture, Viking builders faced a second challenge, one that modern audiences frequently mention. How could walls withstand the winds of the North Atlantic without breaking? The answer was not brute force, but a structural system that archaeology identifies as post and plank. This method has been confirmed in excavations across Norway, Denmark, and the Viking settlements of Greenland, and it continues to impress specialists for its balance between simplicity and effectiveness. The structure began with vertical posts placed at regular intervals. These were not crude stakes hammered into the earth. In contrast to some popular recreations, Viking builders preferred posts set on the dry stone foundation or anchored in protected cavities that avoided direct contact with moisture. Each post had to be exceptionally straight and resilient because it would absorb and regulate the controlled movement of the entire wall. At sites such as Borgund and Trelleborg, researchers have found examples with deep vertical grooves carved with remarkable precision, clear evidence of work performed with well-sharpened iron tools. These grooves were the key to the system. Carpenters carved them into both sides of each post. They were deep, straight, and wide enough to allow horizontal planks to slide into place without becoming rigid. This detail is one that many videos omit, and one that the audience repeatedly demands to understand. The planks were not fixed. Instead, they sat inside the grooves with enough room to expand, contract, and shift in response to humidity or wind. This small margin of movement was not a flaw. It was intentional. The planks were prepared with the same level of care. They were split along the grain to maximize strength. When inserted between the posts, the goal was not to create a perfectly sealed wall. Builders knew that wood in a moist climate changes volume throughout the year. If they fixed the planks tightly with nails or excessive pressure, the wall would crack during the first major shift in humidity or under strong winds. A wall with controlled mobility allowed energy to disperse safely. When the Atlantic winds struck a house built with this system, the wall behaved differently from a modern rigid structure. Instead of resisting as a solid, fixed plane, the planks moved millimeters within the grooves. This flexibility prevented cracks and fractures. Archaeologists and reconstruction specialists in Norway have observed this effect directly during storms. The wall seems to tremble subtly, yet its integrity remains intact. Viewers who commented about breathing walls were describing a real phenomenon, not a poetic exaggeration. The technique had additional benefits. Since the exterior walls did not carry the weight of the roof, they could remain relatively light. Their primary function was to break the wind and protect the interior, not to hold up the structure. Some recent videos misunderstand this point, and viewers have been quick to correct it. It is essential to explain it clearly. Most of the roof's weight was transferred to an internal frame of heavy posts, not to the outer walls. This separation of functions was an optimal solution for a climate with constant atmospheric shifts. Understanding the building process also requires acknowledging the behavior of the materials. Planks made from pine or spruce were often installed slightly green or partially dried, which made shaping and fitting easier. Over time, the wood lost moisture and settled. This natural settling caused the planks to fit even more precisely. Viewers seeking practical explanations will find this particularly relevant. The system improved with age. A plank that initially had a modest margin of movement gradually adjusted to its post, shifting only within the limits needed to prevent stress damage. The grooves themselves sometimes revealed subtle variations in shape. They were not perfectly straight cuts. In several Norwegian findings, grooves narrow slightly inward. This design helped retain the planks more securely and required a specific insertion technique. Builders started at the top of the wall and added one plank after another. Each plank slid downward by gravity until it reached its place. In this way, an entire wall was assembled as a sequence of interlocking pieces capable of withstanding lateral movement without coming loose. The audience has also insisted on practical details regarding carpentry. To carve these grooves, builders needed a specific instrument, the carpenter's axe. It allowed vertical cuts that defined the groove's edges. Then controlled blows removed long strips of wood. Finally, a chisel refined the interior surface. The goal was not decoration, but functionality. A smooth, internal surface allowed the plank to move freely without friction that could cause premature wear. The precision achieved with these hand tools, without modern measurements, speaks to the level of skill these builders possessed. This system also improved moisture control. Airflow between the planks and the internal frame reduced the formation of fungi. This is crucial for understanding why wooden remains found in Viking regions often show surprisingly good preservation. Ventilation was not accidental, it was a built-in feature of the design. Thus, Viking walls were not rigid and brittle. They were dynamic systems designed to adapt. Their capacity to move was the result of deliberate decisions based on available materials, climate, and generations of accumulated experience. This flexibility is one of the most admired aspects of Viking construction today, and one of the features that has most captivated modern audiences. In the next chapter, we will explore the internal structure that carried the tremendous weight of the northern roof. Chapter 3. The Hidden Skeleton. The internal structure that supported tons of roof weight. The audience has often pointed out that many videos about Viking architecture remain on the surface and fail to explain how the interior of the structure actually worked. They want practical, technical clarity, not vague descriptions. This chapter answers that demand directly. A Viking house did not rely on its exterior walls for support. Its endurance depended on an internal skeleton designed to carry tons of weight without nails, without cement, and without a single rigid point of failure. This framework has been confirmed by excavations in Norway, Iceland, and the Faroe Islands, and its performance continues to impress modern carpenters and researchers. At the center of every Viking house stood two longitudinal rows of heavy posts. These were far thicker and stronger than the exterior posts that held the grooves for the planks. They were carved from entire tree trunks, selected for straightness, density, and above all, their ability to support vertical load for decades. Archaeologists at Borgund and at the remains of the farm at Stung have identified deep post holes and impressions in the soil, indicating that some of these posts reach diameters wider than a human torso. Their purpose was unmistakable. They were meant to carry the weight of the roof. These posts were not simply driven into the ground. Instead, they were placed in carefully prepared cavities or set on small stone platforms to avoid direct contact with moisture. Each post had to transfer its load downward evenly and remain perfectly stable. To ensure this, carpenters shaped the base of each post with deliberate, precise cuts, so it sat naturally and firmly on its support. A post that acted like a stake would rot. A post that was balanced, leveled, and protected would endure. The audience has repeatedly asked for clarity about these construction realities, and archaeology confirms that Viking builders rarely left major structural posts buried directly in the soil. Once the two interior rows of posts were in place, builders connected the tops of the posts with transverse beams. These were the first horizontal elements capable of bearing significant weight. The joinery between post and beam did not rely on nails. It depended on carefully shaped wooden joints. The most common was the mortise and tenon. The carpenter shaped a rectangular protrusion at the top of the post and carved a matching cavity in the transverse beam. When the tenon slid into the mortise, the structure locked itself through weight, friction, and precision. Viewers interested in technical detail have asked how these joints were carved. Evidence from preserved Norwegian timber buildings shows the process clearly. Carpenters made the initial outlines with vertical axe cuts. Then they removed the waste material with controlled blows, forming the cavity. A chisel refined the interior shape. The tenon was shaped using a broad-bladed axe to achieve clean, balanced surfaces. A tenon carved too small would loosen. One carved too large would stress or split the beam. The skill required to achieve this precision with hand tools alone demonstrates the level of mastery these builders possessed. Above the transverse beams rested the most important element of the entire structure, the Great Ridge Beam. Archaeology describes it as the spine of the building. This long horizontal beam ran the entire length of the house and distributed the weight of the roof across the interior posts. It had to be extraordinarily straight. Its shape was functional, not decorative. A slight natural curve, in the same way that the keel of a ship curves, could even help distribute stress. At some sites, preserved timbers show that builders deliberately selected trunks with this natural curve. Once the ridge beam was in place, builders added the sloping rafters that formed the framework of the roof. These rafters each connected to the ridge beam through joinery that prevented lateral movement. Here again, the audience has asked for clarification about the use of wooden pegs. Pegs were not meant to make the joint rigid. They were designed to limit unintended movement while allowing the entire roof structure to breathe. A peg, dried thoroughly before insertion, expanded later with humidity and locked the joint in place. It was a system that used the climate to its own advantage. This internal structure shaped everyday life inside the house. Because the walls did not carry weight, builders could create large open interiors without excessive supporting posts. This is why longhouses could reach considerable lengths without collapsing. At Stung, and in reconstructions based on that site, the central space remains open, suitable for the hearth, for work areas, and for communal activity. What modern audiences might call open floor plan was not a stylistic choice. It was a structural consequence. The separation between the load-bearing internal skeleton and the flexible exterior walls offered another crucial benefit. It allowed the walls to move subtly under wind pressure without affecting the stability of the roof. The internal frame acted like a vertebral column, while the walls behaved more like protective skin. This separation of roles is one of the reasons these houses could survive violent storms for decades. It is not myth or exaggeration. It is structural logic. The internal framework also helped support the tremendous weight of turf roofs. The rafters distributed the load evenly, preventing localized collapse. The turf, in turn, kept external moisture away from the timber, while the smoke from the interior hearth coated the upper beams with a protective layer of soot and natural tar. The house preserved itself through normal daily activity, a practical cycle in which warmth maintained the structure that supported that same warmth. The internal skeleton of a Viking house reveals a deep understanding of material behavior. Every component served a function based on predictable mechanical principles, even weight distribution, joints that resisted without stiffening, the controlled use of humidity, and the natural form of the timber. This is why modern timber framers and architects continue studying this system. It works not because it is ancient, but because it is intelligent. In the next chapter, we will see how the Vikings joined every part of this framework without iron nails, and why those joints still impress experts today. Chapter 4. Wood Joinery, the system that replaced iron. The audience has insisted repeatedly on a crucial point. They want to know how Viking builders truly joined the elements of a house. They do not want metaphors, they want technique. This chapter focuses on that fundamental question. The Vikings did not avoid iron nails because they lacked knowledge of them, but because iron was a limited resource reserved for weapons, essential hardware, or tools. For a building intended to last decades and withstand an extreme climate, wood provided a more stable, predictable, and corrosion-resistant solution. Archaeology has demonstrated that wooden joinery was not an improvised substitute, but part of a system designed to work with constant changes in humidity and structural movement. The primary method for joining beams, posts, and rafters was the mortise and tenon joint. This consisted of carving a rectangular protrusion at the end of one element and a matching cavity in another. Clear examples have been found in Viking structures preserved in parts of Norway and in medieval Northern European buildings that inherited this technique. Shaping a straight tenon required a well-sharpened axe and consistent practice. The carpenter made vertical cuts to mark the outline and then removed the excess wood with controlled blows. The mortise was carved in the opposite way, removing material until the fit was firm but not forced. The audience has asked for practical explanations. The key here was adjustment. If the tenon fit too tightly, the joint weakened as the wood swelled with humidity, creating internal stress. If it fit too loosely, the structure shifted. Viking carpenters solved this by carving the tenon slightly narrower on one side. This minimal asymmetry allowed the tenon to expand during the first months after construction, when environmental humidity began to balance with the internal moisture of the timber. It was a joint that improved over time, a behavior the audience has expressed strong interest in understanding. Alongside mortise and tenon joints, the Vikings used another critical element, the wooden peg. This component has been widely misunderstood in modern recreations. Some imagine it as a simple stake hammered between beams, but in reality, it was a deliberate system that used the wood's natural ability to absorb moisture. Pegs were made from denser wood than the beams they joined, often oak, while the surrounding structure might be pine or spruce. This combination worked because the peg, dried more than usual during preparation, would later absorb humidity rapidly and expand, locking the joint securely. To make the peg, the carpenter selected a piece of timber with straight, strong grain. He shaped a dowel slightly larger than the diameter of the hole it would enter. The technical detail, which viewers appreciate, is that the peg was dried near the hearth for days. Wood shrinks as it dries. This allowed the peg to slide into the drilled hole with controlled effort. Once in place, it absorbed moisture again and grew in volume, pressing firmly against the surrounding wood and holding the joint even under storm conditions. Experiments conducted with traditional Scandinavian tools have confirmed this effect. A properly dried peg can create significant lateral pressure as it expands, preventing any horizontal shift even when the exterior walls move under wind. Unlike iron, which oxidizes, weakens, and can corrode the timber around it, the wooden peg integrates into the structure and maintains stability without introducing rigid points that would undermine the building's flexibility. Other, more sophisticated joints also formed part of the Viking toolkit. One important example is the halved joint, used when two beams needed to cross at a right angle. The carpenter removed exactly half the thickness of each beam at the crossing point. When placed together, the two remaining halves created a broad surface of contact that distributed the load across the entire section. This technique avoided concentrating stress in a single point, a necessity for roofs as heavy as those covered with turf. Remains of such joints appear in medieval Norwegian stave constructions, preserving the long tradition inherited from Viking builders. Another commonly used method was the tongue and groove joint, essential when joining boards to create stable surfaces. Although many associate this joint with fine woodworking or furniture, it was fundamental in older constructions. Boards were shaped with one protruding edge and one recessed edge. Fitting them together prevented lateral movement. The joint did not create a perfect seal, but it limited unwanted shifting and allowed the wood to expand or contract naturally without deforming the entire structure. The audience, especially those with woodworking experience, will recognize this as an accurate portrayal of how organic materials behave. The variety of joints was not decorative. Each served a specific purpose. Mortise and tenon joints supported vertical loads. Halved joints resisted lateral shifts in horizontal assemblies. Tongue and groove joints stabilized interior elements exposed to humidity changes. In an extreme climate where timber constantly changed volume, these decisions determined whether a building endured for decades or failed after only a few winters. What makes the system remarkable is its harmony. Wooden joints were not rigid anchors. They allowed subtle movement that complemented the behavior of the walls and the roof. This internal flexibility prevented stress from accumulating at single points. When strong winds pressed against the exterior walls, the energy dispersed through dozens of joints, each offering a minimal but meaningful margin of movement. This detail is especially valued by the audience because it challenges the modern assumption that structural strength depends solely on rigidity. Every part of the system reveals a deep understanding of timber. Viking builders did not seek to make the structure immovable. They designed for movement. Each joint fulfilled a role within a flexible, unified whole, what modern engineers might describe through formulas and stress diagrams. Viking carpenters learned through centuries of careful observation of the climate, the wood, and the effects of time. It is for this reason that Viking joinery continues to impress specialists today. It does not rely on modern machinery, only on knowledge. In the next chapter, we will see how the Vikings insulated their homes using materials that still outperform many modern systems. Chapter 5. The living insulation. Turf, birch bark, and climate control. Inside the house. The audience has insisted on understanding not only how Viking houses were assembled, but how they managed to remain habitable in one of the harshest climates in the world. A structure is useless unless it protects against cold, humidity, and wind. This chapter presents the most distinctive insulation system of Viking dwellings, confirmed by excavations in Iceland, Greenland, and western Norway. Unlike modern industrial materials, this system relied on local resources whose physical properties created a naturally efficient barrier against the weather. The first component of this insulation was birch bark. Archaeologists in Iceland and Norway have uncovered layers of birch bark inside walls and roofs. Birch bark contains a high amount of betulin, a natural compound that repels water. This makes it remarkably impermeable, even after years of exposure. Birch bark does not rot easily, even in constant contact with moisture. For these reasons, it served as the primary barrier against water infiltration in the roof and, in some regions, in the walls. Obtaining birch bark was simple in appearance but required care. The bark was peeled off in large sheets during spring, when rising sap allowed it to detach without damaging the inner layer of the tree. Builders then spread the sheets and let them dry for several days. Once dried, the bark was laid over the upper wooden boards of the roof, each sheet overlapping the next like scales. Here, the audience has asked for clarity. The bark was not nailed down. Instead, it was held in place by the weight of the next layer, a thick, cohesive blanket of turf. Turf was the true thermal insulation. Viking builders cut blocks around 30 centimeters thick, with the grass still attached to the soil and the living roots intertwined. These roots gave the blocks structural integrity, allowing them to be carried without disintegrating. The audience has asked how these blocks were laid and why they worked so well. The method was straightforward. Each block was placed on top of the birch bark with the grassy side facing downward. Moisture and weight created natural adhesion. A second layer was added with the grass facing upward. Over time, the roots continued to grow, knitting the layers together into a continuous, living roof. A turf roof could weigh several tons. This might seem excessive for a wooden structure, but this is precisely why the internal skeleton described in earlier chapters was essential. The heavy interior posts, the transverse beams, and the ridge beam were designed specifically to bear such weight. This heavy roof not only stabilized the building, but enhanced thermal performance. The turf acted as a thermal mass, retaining heat in winter and blocking heat in summer. This principle remains in use today in high-efficiency ecological construction. The audience has also expressed concern about fire risk, especially when seeing recreations where sparks from the hearth rise through the interior space. In a medieval timber building, this would be a serious hazard. However, a turf roof with birch bark beneath it behaves very differently. Birch bark contains oils that repel water, but its layered structure also resists ignition. Turf, especially in the humid climates of Iceland and Norway, retains enough moisture to act as a natural fire retardant. Although the interior of the house could fill with smoke, the risk of the roof catching fire was far lower than many imagine. This insulation system was not limited to roofs. In regions such as Iceland and Greenland, where timber was scarce, walls were also built with turf. Excavations at Lanso Meadows show wall remains more than 1 meter thick, made from carefully shaped blocks of turf. These blocks were placed in an angled pattern to prevent slippage. For viewers seeking practical detail, the blocks were not cemented. Their weight and shape kept them stable, while the intertwined roots acted as natural joints, strengthening the structure as time passed. One of the most fascinating effects of this system was its natural regulation of humidity. Turf soil functioned as a moisture buffer. It absorbed excess humidity from the interior and released it gradually outside. Turf houses were not perfectly dry, but they maintained surprisingly stable internal humidity levels. While the interior could become dark and smoky, the thermal stability remained consistent even during severe winter storms. This explains why many Viking communities adopted turf as a primary building material, especially where timber deteriorated quickly due to harsh weather conditions. Viewers have also commented that many videos ignore the relationship between the hearth smoke and the preservation of the structure. In a Viking house, the smoke did not escape through a modern chimney. Instead, it rose and spread beneath the roof before slowly drifting out through openings in the ridge. This smoke coated the timber with antimicrobial compounds. Over time, soot formed a dark protective layer on the rafters. Although this could be uncomfortable, it preserved the wood from insects and fungal decay. The structure lasted longer precisely because of this constant exposure to smoke. The combination of birch bark and turf also helped maintain interior temperature because it acted as both thermal and acoustic insulation. The relentless Atlantic wind might roar against the exterior, but the inside remained quiet and warm. Reconstructions at Tjodveldisberg in Iceland have confirmed this effect. Even in harsh conditions, the interior temperature remains surprisingly stable. For viewers who have complained that some videos say nothing about construction, this system demonstrates that every decision in a Viking house had a technical and environmental logic behind it. The most remarkable aspect of this system is that it relied on materials taken directly from the environment. It was sustainable, efficient, and easy to repair. If a turf block deteriorated, it was replaced with another. No advanced tools were needed, no expensive materials. A Viking house was designed to live, to adjust with the seasons, and to evolve alongside the landscape. Its living insulation was a work of intelligent adaptation based on understanding nature rather than resisting it. In the outro, we will bring all these elements together to understand why these houses remain models of efficiency and resilience. The house that did not fight the weather. Throughout this journey, we have seen that the strength of a Viking house did not depend on a single secret, but on a complete system in which every decision followed a practical logic. The dry stone foundation protected the timber from ground moisture. The post and plank walls moved with the wind without fracturing. The internal skeletal frame distributed tons of weight with a design that still surprises modern carpenters. Wooden joints worked through the natural expansion of the material, and the living insulation of birch bark and turf maintained a stable interior temperature even in midwinter. None of this was theoretical. It was the result of observation, necessity, and experience. The Vikings built with the resources available to them, but also with a precise understanding of how wood, wind, and moisture behaved. Their houses worked because they did not try to dominate nature. They worked with it. What is most striking is that many of these solutions remain relevant in modern sustainable architecture. Flexibility, natural ventilation, thermal mass, and carpenter joinery are not relics of the past. They are techniques proven over centuries. If you want to discover more about how the Vikings solved challenges that continue to exist in architecture today, and what other innovations have been forgotten over time, continue exploring this world with us. If you want to learn more about how the Vikings faced the climate and transformed wood into engineering, this channel is the right place.